What's up, scholars? Today we're going to talk about right triangles. Right triangles. The first thing we're going to talk about are side lengths that make right triangles. And to do that, we're calling on our old friend Pythagoras. Think about the Pythagorean theorem, which we could only use with right triangles, which said that a squared plus b squared equals c squared. So we can use this fact to prove that the side lengths given could form a right triangle. If a squared plus b squared equals c squared, then we have a right triangle. If not, then it's not. We've got some examples here. Do these side lengths form a right triangle? We've got three sides. Good start. We're going to need three sides to make a triangle. We know that in the Pythagorean theorem, the c is always the longest side, so these are going to be all of our c's. So we're going to check to see if 18 squared plus 32 squared equals 40 squared. Is that true? Let's figure it out. Well, 18 squared is 324, 32 squared is 1024, and 40 squared is 1600. So what do we get when we do 324 plus 1024? Nope. 1349 does not equal 1600, so this is not a right triangle. No! Alright, how about 8, 15, and 17? Let's see. Does 8 squared plus 15 squared equal 17 squared? Well, we know 8 squared is 64, 15 squared is 225, and 17 squared is something 49, right? Nope, 289. What do we get when we do 64 plus 225? Hey, 289 does equal 289. So, yes. And you lovely humans are going to have the pleasure of deciding whether or not example part 3, 6, 7, 9 is a right triangle. All right, the next thing we're going to talk about with right triangles are special right triangles, specifically a 30, 60, 90 triangle, which is called such because its angled measures are 30 degrees, 60 degrees, and 90 degrees. And another special right triangle of 45, 45, 90, again, because its angle measures, you guessed it, are 45 degrees, and 90 degrees. Why are these special right triangles? Well, they have really special relationships with the lengths of their sides. Always, the smallest angle will be across from the smallest side, and the largest angle will be across from the largest side. In a 30, 60, 90 triangle, the side across from the 30-degree angle, which is the smallest side, will be some number. The side across from the 60-degree side will be whatever that number was, times the square root of 3. And the side across from the 90-degree angle, which we know is the hypotenuse, will be 2 times that number across from the 30-degree side, so 2x. So let's do a quick example with our 30, 60, 90 triangle. We've got this 30, 60, 90 triangle here. The side across from the 30 is 4 units long. Let's say 4 feet. 4 feet long, that's the symbol for feet, right? So using these rules right up here, we can figure out the other two sides lickety-split. This says the side across from the 60 is whatever that number was times the square root of 3. So the side across from this 60 is going to be 4 times the square root of 3. 4 times the square root of 3 feet. And this said the hypotenuse was 2 times that number. So our hypotenuse is 2 times 4, which is 8 feet. Pretty cool, huh? Here's a little bit trickier of an example. We've got another 30, 60, 90 triangle, but this time we're given the side across from the 60. And we're going to find the other two sides. We know the side across from the 60 is the smallest side times the square root of 3. But this has no square root of 3 in there. So to figure out what the smallest side is going to be, we'll divide 6 by the square root of 3. 6 divided by the square root of 3. Now, way back when we didn't have calculators, this was a horrendous task to do because you're dividing by an irrational number. So we developed this thing called rationalizing the denominator, where we multiply the numerator and the denominator by the square root of 3. Why do we do that? Well, the square root of 3 times the square root of 3 is 3. How does that happen? The square root of 3 times the square root of 3 is the square root of 3 times 3, which is 9, and we know the square root of 9 is 3. So we no longer have a square root in the denominator. Now, how do we do this 6 times square root of 3? We just do 6 times square root of 3. So that's just 6 times square root of 3. But then we say, hang on a second. I could divide this 6 on the outside, nothing on the inside, leave that guy alone. 6 on the outside by 3. 6 divided by 3 is 2. So our final answer here, this is 2 square root of 3, which is how long our smallest side is. 2 square root of 3. So now we know what that x is. That small side is 2 square root of 3. We need our hypotenuse still, which is going to be twice as big as that. So we're going to take 2 times the outside, this outside 2, 2 times 2, so this hypotenuse is now 4 times the square root of 3. Cool. All right, let's look at this 45, 45, 90 dude. Again, it's called a special right triangle because it's got some special relationships. These angles are the same, so these sides are going to be the same. This is an isosceles right triangle here. So both of these sides will be the exact same number. And the hypotenuse is going to be that number times the square root of 2. Cool. You know what time it is? It's example time. This little tiny baby example. This is a 45, 45, 90. How do we know? Well, these angles are equal to each other. And all the angles have to add up to 180. That guy is 90. So these two have to add up to 90 and be equal to each other. So they have to be 45 degrees. So this is a fast way to see, or to show this is a 45, 45, 90 without putting any numbers in there. All right, let's figure out the other two sides of this triangle. This says the two sides across from the 45 degrees are the same number. So these two sides are going to be the same number. So this is also going to be 3. And this says the hypotenuse is that number times the square root of 2. So this is 3 square root of 2. Cool. Let's do one more trickier one. All right, this time we're given the hypotenuse, which is supposed to be the smaller side, times the square root of 2. So to figure out what the smaller side is, we are going to divide by the square root of 2. So we'll do 10 divided by the square root of 2. Same thing I did here. We multiplied by the square root of 3 over the square root of 3. So we're going to multiply by the square root of 2 over the square root of 2. And when we do that, we'll get, I'm going to keep going down that way, 10 times the square root of 2 on the top is just 10 times the square root of 2. Following this logic, where the square root of 3 times the square root of 3 was 3, the square root of 2 times the square root of 2 is going to be 2. We see that we can reduce, because 10 divided by 2 is 5. So this is 5 square root of 2, which means these two smaller sides are both 5 square root of 2. Nicely done, beautiful minds. Our last topic for today are right triangles and the geometric mean. It's not really mean, it's actually pretty cool, this thing, geometric mean. Anyway, let's say we have a right triangle here. It's got a 90-degree angle and then 2 other angles. Now, if I, from this right angle, draw an altitude, meaning a line that comes down and makes a right angle with that side, I've actually made 2 similar triangles to that big, giant one. How, you say? Well, let's look at this little guy for a second. This little one, we're looking at over here. This little triangle has a right angle, just like the big one did. It has that pink angle, just like that big one did. So we know that the smallest angle in this little triangle has to be the same as that blue angle, because they have to add up to 180 degrees, and there's no other way to do it. If they both have a right angle and they both have that pink angle, those third angles must be congruent to each other. By a similar logic, if we look at this middle-sized triangle, it has a right angle. It has a blue angle. So its third angle must be the same size as that pink angle. Oh, so cool! So now we see we have three similar triangles, which we could write out a similarity statement. How about the big one, triangle ABC? Triangle ABC is similar to, A was the blue angle, so let's look at this little one. If A was the blue angle, then it's going to be triangle BDC. BDC is similar to this guy over here. And again, we started with angle A, which was the blue angle. So this will be triangle ADB. ADB. And then we can use some relationships of sides to figure out missing sides. Okay, cool. So here's our example. We have the exact same situation we just talked about. We've got a big triangle split into two smaller triangles, which we proved above are all similar. We're going to use that information to solve for this y. What is y? Well, y is the hypotenuse of the big triangle. We need some proportions here to match some sides up. So we know we're looking for the hypotenuse of the big triangle. Do we have any other hypotenuse information? Yeah, we have the hypotenuse of the left side of the triangle. We also have the larger of the two sides of the big triangle. That's not the hypotenuse, right? So we have the larger leg. And we have the larger leg of the left triangle. So let's do a hypotenuse over a leg ratio. So of the big triangle, what's the hypotenuse of the big triangle? Well, that's the y that we're looking for. What's the leg of the big triangle? Well, that's 6. That's going to be equal to the ratio of the hypotenuse of the left triangle, which we know is 6, over the leg of the left triangle, which we know is 5. Cool. Now this is called using the geometric mean, because these numbers are the same. They will always be the same. The bottom of one side of the proportion will be equal to the top of the other side. So geometric mean, these numbers should always be the same. If they're not, something funky happened and you set up. So we solve this real quick. These numbers should be the same. We solve this real quick. We're going to cross multiply 5 times y. It's going to be 5y. 6 times 6 is 36. Divide by 5. Divide by 5. We get y equals 36 divided by 5. We'll pull out our handy dandy calculator. And we get 7.2. All right, let's do another example of these. These are a little tricky to wrap your mind around. So we've got the same situation. I should give this a right angle here, though. We have a big triangle. We have two little triangles. We have information about the hypotenuse of the little triangle and the smaller of the two legs of the little triangle. We are looking for the hypotenuse of the big triangle. And, hey, look, we know the smaller of the two legs. So let's do hypotenuse over leg again. Let's do the big triangle and the right small triangle. The hypotenuse of the big triangle, that's what we're looking for, y. The smaller leg of the big triangle is 4. That ratio is going to be equal to the hypotenuse of the right triangle, which is 4, over the leg, which is 2. Again, geometric mean says these two numbers should be exactly the same, so we're spot on. Cross multiply, we get 2y equals 4 times 4 is 16. Divide by 2, and we get 8. Easy peasy, lemon squeezy. All right, scholars, that is it. I love you. Great job. Stay beautiful. come to office hours, and see you next time. Peace.